Welcome to Capel's column. Today, we're going to talk about the use and the abuse of the PCR test. Why is this test so important in the current situation in the world? Because it is used to detect infectious material, and it is the basis of all measures taken to prevent COVID-19 infection. But everybody is told that there is a second wave. And if you test with the PCR, in the current situation, in the current way, it looks like on the right side, it is really a heavy wave and something is really rotten in the state of Denmark. But on the other hand, if you don't go for the PCR, but just for the medical situation where people are getting ill or even can die, what is that number? And if you also test the real presence of the virus, then the second wave looks totally different. Perhaps I exaggerate a little bit on the left-hand side that it is totally flat. No, in autumn there is always a little bit of coronavirus which comes up and then goes down again. If we're going to talk about the PCR test, does it detect live active virus? And there are many, many studies, and this is one of them in the Lancet, recently published in November, that what is stated here is that even in the past, there are samples of SARS-CoV-1, SARS-CoV-2, MERS, and so on, that they checked whether there was an infectious sample when the PCR test was positive. What they found is that the positive PCR test was indeed, or could indeed, test RNA, which was shedded in the respiratory samples they took. And that was measurable for weeks and months after infection. However, viable live virus, so the real infectious virus, is short-lived. And all these studies prove that live virus, so infectiveness, or whatever you want to call it, is gone within 8 till 9 days. So the positive PCR test cannot discriminate between live virus and some leftovers of a virus. Once I heard a Dutch scientist say that a PCR test, which runs with a lot of cycles and only tests fragments of RNA present in the noswap, is comparable that the police is looking for a car which was involved in a crime. It was a black Mercedes. So they go into the scrapyard and there they find one steering wheel and the hood, a black hood of a Mercedes. And they say, oh, we found the car. Well, in that way, you have to look at the PCR. However, it's even more serious. I'm going to shut this off. The PCR test, that is this one, which is used very commonly all over the world, is created in a hurry in January before everything was really clear and even before the pandemic was declared. That test has a lot of difficulties. Here is a whole bunch of fantastic scientists which all have a profound track record in the field of PCR. They studied the way this test was prescribed and which is done all over the world. And what they found is that there are 10 major scientific flaws. And they are so major that they result in a lot of false positive results. I'm going to explain the whole PCR principle and the pitfalls But let's first start how to take a sample. What is a nose swab? You go into the nose with this little stick, but there is not only some virus or no virus, there is your whole microbiome. And microbiome is the whole bunch of bacteria, viruses, fungi, and you name it. But besides microbial stuff, there's also house dust, there is pollen, there is all type of air pollution, also in your nose. And you take a sample of that. Then what you do is that in this nose swab, there are these microorganisms, there is all type of dust, there are fungi and whatever. Do you have to worry about that? No. This is the normal protection in your body. So in your gut, you have tremendous amounts of bacteria, viruses, fungi, you name it, but also in the nose. And they protect you for a lot of good reasons. So you take a sample, then you make, from the RNA present in it, you make DNA. And here you see a whole bunch of genetic material coming from all type of organisms. And the question is, which one is really corona? Let's say that this little piece is corona RNA that is transferred into DNA and that you want to see if it's present in the context of all the other genetic material which you are not interested in. So you highly specifically have to pick out the corona RNA, or which you has already transferred into the DNA form. You do that with a very specific genetic code, which is the mirror image of a code present in your sample. These pieces of genetic material bind to each other, and then that is called the primer. And then you start the PCR reaction to detect this little amount of DNA, which you convert into a huge amount. The polymerase chain reaction is a beautiful technique to detect a very small sample of genetic material in which you are interested, and in our case, a virus. You do that by taking a sample, the nose swab, and because it's RNA, you change it into DNA, put it in a PCR machine, and then you copy the part you're really interested in. So here in green, you have the target DNA, which you want, and you heat up the whole stuff up till a very high temperature by which the DNA strands denature, they separate, and you get two single strands. Then you add an enzyme, which is called polymerase, and that can copy these strands. But where do they start? The starting point is called a primer, and that is a very specific genetic sequence which specifically binds to the part of DNA you're interested in. Then you change the temperature and start reproducing the DNA. So you copy the DNA you're interested in and a little bit more, but it doesn't matter. Then you stop and go to the second cycle. You denature, so you separate the strands, you add the primers, selectively they bind to the piece you are interested in, you change the reaction conditions, and oops, there it goes. So you multiply the green part of DNA and also a little bit of the adjacent parts. But if you do that for the third time, and you add the whole rigmarole again, and you start to copy, you get an awful lot of your DNA which you are interested in. And after each cycle, this goes exponentially, your piece of DNA is being multiplied. But that goes very fast. So first you have a couple of copies, but then it goes exponentially. And cycle after cycle, you get more and more of this green piece of DNA. And so you multiply, and it goes in the hundreds, in the thousands, and it goes in the millions and the billions. And so after each sample, you amplify. But after 30 cycles, you have copied 1 million times the original amount of DNA you were interested in. But if you start this highly sensitive reaction in which you amplify one molecule more than 1 million times, or even much more, then the starting point is very vital. So the quality and the purity of your primer is from utmost importance. So we have a machine, you can program it, and it makes all type of nucleotides in the sequence you want. So A, T, T, G, A, etc. The machine is doing that automatically. However, it is possible that in this machine, one of the little drops or steps takes a little longer, and then you get this situation. And now let's look very precisely. Here you have 1 T, and here 2. Does that make a difference? Yes, that makes a very big difference, because now this primer, which looks like, but isn't like, doesn't detect COVID-19 anymore, but something else. So now we're going to do the test, and the primer is not entirely pure. That means that you also amplify a piece of genetic material you have no idea what it is. And in this way, you get a positive reaction, but you don't know whether that was from corona originally. You don't even know whether it's a live virus, and you don't know what you're really amplifying. So the primer is really very important. What is really important? We go to a little story where a king wants to reward somebody, and the person was asked, "What do you want to have?" He said, "Take me a chessboard, a board of chess, put on the first field 1 grain of rice. On the second, 2, then 4, 8, 16, and so double." And this is an exponential multiplication of the grains of rice. The king thought, well, it's not so bad. But in the end, when he came to the last fields, it was impossible to find such an amount of rice which is amplified in such a high way that you cannot cope with these big numbers. So if we start with 1 molecule and we go into 20 cycles or laps, then you amplify 1 molecule 1 million times. If you do the same but continue to 25, this 1 molecule is amplified 16 million times. And if you go to 35 laps, it's 35 billion times. So this exponential growth of the number of molecules is phenomenal. And therefore, the number of cycles, the amount of amplification is really critical in the positive or negative judgment of the test. Say if you have a small impurity, we have 2 little molecules you don't want, but they are there. Then 2 is getting 4, 8, 16, 32, 64, and in no time you have a big heap of DNA, which is the amplification of an impurity. The PCR reaction itself doesn't only measure the amount of DNA formed, but does not discriminate from which origin this whole heap of DNA came from. So this can be viral DNA, but can also be something totally different. And the only thing the test is measuring is the synthesis of this big heap of DNA. So with a small impurity, you already have a false positive. However, in the test used, the temperatures, the primers, the number of cycles, and all other conditions, they are highly questionable in the way it's performed at the very moment. And the chance that you are just measuring false positives is very, very big. When somebody is infected with COVID-19, this pattern of infection can differ from hardly any symptoms at all to quite a lot of symptoms. Normally, people after infection are called asymptomatic. They have a little problem or no, a little fever or no, and after a few days, they are happy on their feet again. If you measure the whole virus, which is infectious, how long can you detect that with viral cultures after the infection? And that amounts to 8 days. After that, you still can have a positive PCR test, but it doesn't measure the whole active virus, but the pieces of viral RNA, and they are detectable for a very long time, weeks to months. So if you do the proper PCR, up till 24 cycles and not more, and you do it in the time frame of about 1 week after infection, then your positive result can very well be an infectious virus. However, that's not how the practice is done. So instead of looking really for virus, they have amplified the number of cycles. They changed the type of primers, and a lot is very, very questionable. So with a asymptomatic infection, that if you cannot find a positive signal after 24 cycle, then the chance to really detect an infectious virus is very, very small. But if after 25 cycles, gradually the test becomes positive, it is either possible that you demonstrate a non-infectious virus RNA piece, or it's possible that it's totally something else. You don't know. But this doesn't give you any clue about infectivity or not. Now, so it could be viral RNA, it could be whatever, but you don't know. If the test really becomes positive at 35 cycles, then it is beyond belief because it says absolutely nothing. So how the test commonly is done is very, very questionable. So what is the only effect of a test which only becomes positive at 35 cycles? Well, although the PCR is fantastic, but in this way, the only thing which is generated is anxiety. I would like to summarize that we are almost like the rabbit sitting trapped in the headlights of the PCR reaction. And inside this small little vision is created our new normal, which goes beyond the real reality, which is outside this tunnel vision. Here are the areas where people really suffer, are lonely, become suicidal, become anxious. The whole economy is ruined. And for what? Is the pandemic really as pandemic as they said in the beginning? Now the WHO has changed its view, but that is still not taken into account. We are still leaning only on this PCR reaction, which is in principle fantastic, but currently misused. I wish you a very thoughtful day.